Okay, the second problem that I mentioned in the outline is this one. Okay, we have two species. One species we name the variable for it as x, another one as y. So the population changes as time changes. Okay, the assumption here is that they compete with each other. Okay, means species x with x compete for food. The second assumption here, in the absence of either species, means for species x, if y species absent, they would grow as a natural rate. And the third assumption here, no interaction or competition between the two species, means between x and y there is no competition. Okay, so this is the model for this. The first assumption here, if we consider the population changes for x, means we will have the first equation, the equation for the x dt. And this assumption means x compete with x for food, the same with y compete with y for food. Okay, so it's some kind of if we see in the predator prey, we have competition x and y. Okay, but now this is competition with the same species. Okay, so due to this competition, it may lead to the decline of the population. Okay, so in the equation, actually you will see this term, negative b1 x squared. Okay, so if we consider the x equation, we will have negative of x squared. Okay, so species x interact with or compete with another x. That's why we have x squared. And if we consider the equation for y, we will have the second term here. Okay, the species y compete with another y species. Okay, there will be competition between y and another y. So that's why we have the term negative. Negative means the population may decline. Y squared is the interaction between the two same species y. The second assumption here, in the absence of either species, the other species would grow at natural rate. Okay, so means here for equation for x, this is the same as in the quite similar with predator prey. Okay, we can relate with the problem, the previous problem. Absence of y here, so species x may grow at natural rate, so that's why we have in the equation positive a1x. Okay, so this is represented by positive a1x in the first equation. So for the second equation, for y population, means absence of x, species y would grow. Okay, so we have the second term, the first term in the second equation is a2y, because it may grow at a natural rate. Okay, so that's why in this equation we have two terms each. Okay, I don't have example for this. I proceed with the next problem. Okay, next problem, the last problem in this outline. Okay, in addition to the assumptions in problem 1. Okay, so actually in problem 1, I mentioned that there is no competition between the two species, means species X and Y. Okay, so now if we have the competition between X and Y, okay, if we see here, the first and the second term is actually the same as in the previous problem. It is the competition between here competition between the same species. Here is growth at a natural rate. So now if we consider the third assumption, exists the competition between the two species. Okay, it leads to decline in each population, proportional to the product of the two species frequency of encounters. Okay, so this is represented for the X species. It leads to a decline, so that's why we have negative C1 here. Competition here is between two different species. So species X compete with species Y. Okay, frequency of encounters, so X multiplied with Y. Okay, this actually similar. This is frequency of encounters between the two species X and X. Okay, so here X and Y decline negative. So the third assumption here represented by negative C1xy in the equation X and negative C2xy in the equation for Y. Okay, so there are some interesting cases actually for this problem. The first one is a survival of a single species. This happen actually if in the equation we have the constant here, constant for C1 multiply with C2. Okay, let's say we have certain number for all the constants here. Then if we check the value here multiply with the value here, we check with the value here multiply with the value here. Okay, for this case C1 C2 when it is greater than B1 B2, we can see from, okay, if we see the phase portrait for example, or we solve it using the eigenvalue method, we able to see the pattern of solution or long-term solution actually, the type of survival of a single species. And for the second case here is if the value for C1 C2 is less than B1 B2, we able to see the pattern of long-term solution is actually peaceful coexistence of two species. Okay, the meaning here, survival of a single species means in a long run only one species managed to survive. Okay, but for the second case here, uh, both species able to survive. Okay, peaceful coexistence even though there is competition between the two species, but they manage to survive. Okay, I would say that this is actually the most general one for the problem of population related with the nonlinear system. I would say this is the most general one. So actually if you begin with this form of equation, okay, you understand each term here. The first term is the growth of each population or species at a natural rate. The second term is due to the negative if we have competition between the same species, X with X, here Y with Y. And the last assumption, the last term here comes from the assumption negative means decline due to the competition between the different species X and Y. Okay, so actually in some books they mention this form of model for the problem is the most general one of the competing species problem. So from this general one, okay, actually we can reduce to many problems actually. For example, if we don't consider the third assumption, means from this equation the last term will not appear, so there will be the the previous problem that we see. Okay, and for the second problem as well, there is also some cases about the sign for the constant also can be positive or negative. Actually, it depends on the equation. Okay, I will show in the example that I will choose some examples from the past year's question, okay, to show how the model, the problem related with the equation. Okay.